Okay, next we discuss the properties of kits, bras and bra-kets. The, the first property is like for every cat there is a corresponding bra. Like for every cat psi there should be a corresponding bra given by this one. Now the relationship between a bra and kit is given by this equation. Suppose we have a kit, this will be equal to the bra if we take the complex conjugate of this kit. And also if we have a kit A of psi and we take the complex conjugate of this whole kit, we get a bra vector which is A steric psi. This is another property where A is a complex number. Similarly, if we have a complex number inside a kit, then we can bring it outside of the kit and write it as like this. Similarly, if the complex number is inside a bra, then we can bring this complex number outside of the bra vector, but we have to take the complex conjugate of this complex number because this represents a complex conjugate of a kit vector, and we have this relation. This was the first property. Now the second property is the scalar product of psi with phi is not equal to the scalar product of phi with psi. But the scalar product of psi with phi, if we take its complex conjugate, will be equal to the scalar product of phi with psi. Now we will prove this property now. As we know that the scalar product psi with phi in coordinate representation can be written as integral of psi steric, which is a function of both position and time, phi, which is a function of both position and time, and d cube r. Now if I have to take the complex conjugate of this scalar product, then I have to take complex conjugate of the right hand side also, which is psi steric r over t, phi, and d cube r, and we have the complex conjugate here. I just take the complex conjugate of both sides. Now this side is equal to, as we know that if we have two functions, two matrices A and B, if we have to take the complex conjugate of these two matrices, then we will get B steric, A steric. We have to change the order of the matrix product, and then we have to take complex conjugate of each of them. Also, if I have a matrix and if we take double complex conjugate, then we get the same matrix again. The same is true for the functions also, or for the state vectors also. So here I will first apply this property and then I will apply this property. So if I apply this complex conjugate, I will get phi steric, psi steric. One steric is itself and the other sterics come from this one, and then d cube r. Now this is equal to phi steric, and then we will apply this property here. the complex conjugate, and again taking complex conjugate, we will get the same state vector psi r over t, and then d cube r, and this is equal to phi or psi, the scalar product of phi with psi. So the scalar product of psi with phi whole complex conjugate will be equal to the scalar product of phi with psi. This is another property of bra-ket, bra-ket. The third property is, if we have a bra psi and we have a ket a1 psi 1 plus a2 psi 2, which is a linear combination of two state vectors psi 1 and psi 2, then this will be equal to, we will take the scalar product of psi first with this one, which is a1 psi 1, and then plus the scalar product of psi with this one, which is a2 psi 2. We already mentioned it before that if we have a complex number inside a ket, then we can bring it outside of the ket without changing the complex number. So the same is true here. A1 is with the ket, so we have to take it outside of the ket, and we left with psi 1 plus, and similarly A2 is here with the ket, so we'll bring it outside and we left with psi 2, the scalar product of psi with psi 2. This is another property. Now if I have to change the order, the fourth property is, if the scalar product is such that a1 psi 1 plus a2 psi 2, this is a bra vector and we have the ket vector psi, then first I take the scalar product of a1 psi 1 with psi, then a2 psi 2 with psi. So this is a1 psi 1, scalar product of a1 psi 1 with psi, plus scalar product of a2 psi 2 with psi. Now if a complex number is inside a bra, then we will bring it outside of the bra by taking its complex conjugate, and we have the bra vector psi. I will apply this property here. Now a1 is inside a bra, this is a bra vector, so I have to take it outside by taking complex conjugate, and we'll left with scalar product of psi 1 with psi, plus a2 steric, taking it outside of the bra vector, so we have to take the complex conjugate, times psi 2 psi 1 psi. This is another property. Now the next property is the norm. The fifth property is the norm is real and positive. What it means? Suppose we have a state vector psi which belongs to the Hilbert space. Then the scalar product of psi with psi is always real and positive. For example, we have two complex number a plus iota b, and other complex number z1, and this is z1. Then z1 steric is always a square plus b square, which is always greater than 0, and it's always a real number. The same is true for the state vectors. The scalar product of state vector psi with itself is always real and positive. Also, we have another sub property. The scalar product of psi with psi will be equal to 0 only if the state vector or the ket psi is 0, and if the scalar product of a state vector psi with itself is equal to 1, then this we can say that the state vector is normalized. We already discussed this property in the Hilbert space. Now the next property is, suppose we have two kets or two state vectors psi and phi belongs to the same Hilbert space. Now if the scalar product of psi with phi is equal to 0, then we can say that psi and phi are orthogonal. We also discussed this property in the Hilbert space. Now this is another property, okay? This one, this is orthogonal property or orthogonal states. The next one is orthonormal states. If we have two state vectors psi and phi, they belongs to the same Hilbert space, such that the scalar product of psi with phi is 0 and the norm of, or the scalar product of psi with itself is 1 and the scalar product of phi with itself is 1. Then psi and phi are said to be orthonormal. This is another property. Like the state vectors are orthogonal and they are normalized. Because they are orthogonal because their scalar product of psi with phi is 0 and they are normalized because the norm is equal to 1. Then these two state vectors are said to be orthonormal. Now we have some restriction here. If the forbidden quantities, we will discuss the forbidden quantities. If psi and phi belongs to the same vector space, then the product psi phi is forbidden, and also the product psi phi is forbidden because this product is neither ket neither a bra. But if psi belongs to, if the ket psi belongs to one vector space or one Hilbert space H1 and the ket phi belongs to another state vector space or another Hilbert space, then the scalar product psi and phi are allowed and they have some meaning. What it means, like psi phi can be written as psi and we have this notation phi, and this is called tensor product. But we are not going into the detail of tensor here. We are just considering the state vector, so we are not in business to this one. So I will left this one, and up to this point we discuss the properties of state vectors. Thank you.